Today my talk is on strong noise measurement of lithium aluminate strontium titanate electron waveguides. Correlated electron systems has been revealed to have many interesting properties, such as superconductivity and ferromagnetism. Nanoelectrics help us to design quantum devices, leading us to investigate quantum simulation, quantum transport, quantum sensing. Oxide heterostructures provide us with the opportunities to study these properties on nanoelectric devices. They offer opportunities for extending the paradigm of quantum transport beyond the realm of traditional 3-5 semiconductor heterostructures. In our lab, we study LAO-STO heterostructure, which have interesting electron correlation effects. Both LAO and STO are insulators by nature, but when we put a thin layer of LAO on STO, the electron gas forms at their interface. This 2-DAG has variety of interesting properties, such as high mobility, metal-to-insulator transition, magnetism, tunable spin-orbit coupling, and superconductivity. And recently, we discovered that there is electron pairing without superconductivity in this system. By placing just under 4 unit cells of LAO, we can control the transition between conductive and insulating by conductive atomic force microscope lithography. We put a thin layer of LAO on the surface of STO and get a 2-DAG at the interface. We deposit gold and titanium. We deposit gold titanium electrodes to make contact with interface. Then we use conductive AFM to pattern our devices. When we sketch with positive voltage on the tip, it leaves photons on the surface of LAO, which attract the electrons to the interface, thus make a certain area conducting. The wires we wrote can be as thin as 2 nanometers. When we apply a negative voltage, the tip can erase the device, which enables us to make barriers at the interface. This whole process does not modify the crystal structure of LAO-STO and can be repeated as many times as you want. We exploited the CAFM technique to write electron waveguide on LAO-STO interface. The length of the main channel of our waveguide is around 1 micron. We first write with a positive voltage and then repeat with 2 dips in our voltage function to make these 2 highly transparent barriers, which isolate the system from source and drain and allow us to train the chemical potential by Seagate. This picture shows the effect of Seagate to change the chemical potential of our waveguides, thus change the number of occupied subbands. Each occupied subband contributes 1 square of H to the conductance of our waveguide. So there should be plateaus of multiples of E square over H in its conductance. The red pictures are the experimental data we got. We can see clear plateaus in the conductance data, and the transconductance data maps out the bottom of each subband and resolves the lateral, vertical, and spin degrees of freedom. These features show that our LAO-STO waveguides are almost consistent with non-interacting band model. However, as we zoom in and look at the transconductance more carefully, we notice other interesting phenomena such as pairing, avoid crossing, and reentrant pairing of electron subbands. These features appear in the same parameter space as the non-superconducting Cooper pairs previously observed in our single electron transistor. We can see when the B field is larger than the critical field for superconducting, the electrons are still paired together. This phenomena can be ascribed to strong electron correlation at LLS2 interface. So how can we determine the electron state of our waveguide without sweeping circuit or magnetic field? The answer is strong noise measurement. So Schottky first measured strong noise in a vacuum diode. Because the tunneling process is a Poisson process, the spectral density of the current noise is 2EI, where I is the current with a final factor of 1. The final factor is defined to be the ratio of the strong noise to what the strong noise would be in the Poisson limit. Sub-Poisson or super-Poisson noise indicate some interesting correlation between charge carriers. So in our electron waveguide, when only one electron is occupying each subband, we get conductance to be E square of H times the transmission eigenvalue, and the noise spectral density is this, and this is the final factor. But when the electrons are paired, this is the conductance, and we can see the noise spectral density is 4 times larger than the regime when the electrons act as individual. So there are two kinds of experiments we can do. We can first change the circuit and vary the transmission probabilities, and the strong noise expected to have maximum whenever the transmission of the uppermost connecting channel is 1/2. And we can also vary the source drain voltage. The strong noise of a paired waveguide system should have double the slope of an unpaired system. So here is like a graphical illustration of what we expect when we change circuit. We should see the peaks when the transmission eigenvalue are 1/2, 3/2, and 5/2, etc. And below is a previous measurement done on a quantum point contact. We can see that there are indeed the noise spectral density indeed have peaks when the transmission probability is half integer. And second, we can vary the source drain voltage. We can see the paired regime should have double the noise spectral density compared to the individual regime. And down below is a previous measurement done on a superconductor normal metal junction, and they see this double Poisson noise. So here's the experimental setup we used. We connect two low temperature amplifiers to the two ends of our device, and we connect their output to a differential amplifier. And there's also a stage of warm room amplifiers at room temperature, and we use a high frequency diode to convert the noise to a DC voltage, and we add the output, we do a lock-in measurement. So this is the data we got. We can see that we are able to use circuit to train the conductance of our device, but we cannot see the clear plateaus because the mixing chamber temperature is really high because of the RF cables we use to connect the mixing chamber and the amplifiers at the 4K stage. And on the right is the noise data we get, the output of Schottky diode we get. And we can see it did increase with the source drain voltage, but the different colors represent different circuit value, and we cannot see any dependence on side gate voltage. So there's still improvement to be carried out on our measurement system. So first we can use the superconducting coax cable to reduce the temperature in emission chamber, and we can add some bias tees to reduce the noise of our system, and we can also use a LCR resonator to pick out the signal at the frequency we want and solve the impedance mismatch. And we can finally, last but not least, we can do a gain calibration of the whole system. In conclusion, there is strong electron correlation in the 2D electron gas at LLSTO interface, and we can use short noise measurement to understand the mechanics of this electron correlation.